Some of the topics that Libby and Claire and others have been talking about addressing during this webinar series involved everything from soup to nuts about the program, why Jezero Crater was chosen, what we knew about it before we went there, what we've learned with the Perseverance rover, how we are selecting the samples, what kind of context we know before they even get back. How are we actually doing that sampling? How does that caching system work? And how will we get those back safely? For those of you who came to listen to me and Aaron talk about the OSIRIS-REx program, as you know, this is a really interesting way of doing in situ work by bringing back home to your lab. We're going to talk about the preservation and curation process of these samples, the mission architecture so that you can plan out your next couple of decades. And of course, we'll talk about planetary protection and contamination concerns with these and how we're making sure the sample's safe. There's all sorts of other topics that I don't have on this slide that Libby and others have been thinking about adding to the webinar series. So please let us know if you have ideas or things that you're curious about with the program so we can add that to the list. As everyone knows, after the two presentations, we have about a 10-15 minute discussion, Q&A period. And then the steering committee, we're hoping that you'll all join us for another 20-30 minutes of open collaborative discussion where we talk about ways we can identify benefits, challenges, and opportunities for those of us working in life detection science. So with that, I'll hand it over to Libby, who probably knows how to use Zoom better than I do. Literally anybody knows how to do that better than I do.
Thanks very much, Heather. I'm delighted to welcome our two speakers today, Dr. Briony Horgan and Dr. Sunanda Sharma. So as Heather said, we have this webinar series planned out. And for the very first one, we wanted people to get a really good background on Jezero Crater. And so we have Dr. Briony Horgan with, among other things, an orbital perspective on the crater. And then Dr. Sunanda Sharma will be talking. She's a member of the Sherlock team, so both Sherlock and PIXL data from the crater. And so Briony did her bachelor's at Oregon State and PhD at Cornell University, and then she was a postdoctoral fellow at Arizona State and is now a faculty member at Purdue University. She's been on a number of missions, including Themis, a participating scientist and collaborator on MSL mission, and then a long-term planner and tactical science lead and co-I on ZCAM on the Mars 2020 mission. She's published many papers on Jezero Crater, including one from an orbital perspective looking at evidence for possible lacustrine carbonates on Mars. And so with that, Briony, I'm happy to hand this over to you for your presentation.
Sure, thank you. I'm glad to be here. This is a really cool group, and you guys are, it sounds like a really useful discussion, so I'm happy to contribute however I can. And so I have 25 minutes is the goal? Okay, I'll try.
Yes.
Okay. Feel free to ask questions for clarification or something if you'll need it. Okay, so yeah, so Jezero Crater. Okay, so what do we know about Jezero from orbit? And did we get it right, at least so far, based on what we've seen? So of course, this picture you can see on my title slide is one of our views in, no, sorry. I don't know. Anyway, one of our views in Jezero Crater, looking across the crater floor to the crater rim. There's lots of great geology in here, and we'll talk about some of these pieces as we go through. Of course, here's the Perseverance rover, extremely challenging, fast-paced mission. We like to call our rover a roving astrobiologist in a lot of ways, but it's also a roving geochemist, all kinds of things, right? But we have a very challenging task where we're trying to do our best to identify biosignatures on another planet in situ, and also collecting samples for potential Mars sample return. Of course, here we see the Ingenuity helicopter 2, which is still going along on Mars with us. And then, of course, the instrument that I work on specifically is Mastcam Z, which you can see down here on the left. It's the two main science eyes of the rover that give us most of our beautiful, colorful images that we see. So, but here's the context. And so here's where Jezero Crater, which is our landing site, is located on Mars. So on the left, you can see what is sort of the default global map of Mars. So that's topography, where red is high, blue is low. And so Mars, of course, one of the major defining features is this huge dichotomy boundary between ancient rugged southern highlands and the smooth northern lowlands. Jezero Crater is actually kind of right on that boundary. It's actually on the edge of the Isidis Impact Basin, which dissects that boundary. And so you can see on the right, the Isidis Impact is this big, bite taken out of the boundary over here. The Isidis Impact actually defines the beginning of the Mars geologic timescale. We think at about 3.9 billion years, but nailing down that date is one of the goals of Mars sample return. So we'd like to actually figure that out. But Jezero Crater, you can see, let me see if I can get my mouse to show up. This is. No. Okay. No, that's okay. All right. So Jezero Crater is right on the edge of Isidis. You can see it's really kind of between some of the major rings of the Isidis Basin. It's also right on the edge of Syrtis Major, which is another major volcanic complex, which postdates a lot of the rocks that we'll be talking about in Jezero Crater, we think. Okay, so Jezero Crater. I don't know why I can't do anything with my mouse. It's so annoying. That's okay. Can you guys see the screen okay? Nothing's blocked or anything for you? Okay, great. Then I'll keep going. Yeah, so here's Jezero Crater. So this is from orbit with our MR context camera, CTX, a nice mosaic. So it's about a 45-kilometer diameter crater. And of course, the really important characteristic of it is that it's actually has both a major inlet channel coming in on the west there, feeding what we assume is an ancient river valley that cut through the rim to feed into a potential lake in the crater, and then actually an outlet channel up on the upper right as well. So at one point, it was an open basin lake. We know it was a lake because it actually has this beautifully preserved delta-like fan-shaped feature over here on the left, which we tend to call the Western Delta. Now on the mission, we try to go for fan or something a little less genetic, but still delta tends to stick for most people. But you can also see some of the other characteristics of Jezero in here too. You can see the rim on the west is pretty well preserved. It's kind of gone for most of the east and north. But the west, where we will actually hopefully get to investigate it pretty soon, is still pretty well preserved. And you can also see the crater floor down here, this kind of sort of crater dark, almost looks like a flow flowing across the crater floor with all of these lobate edges. That's what we call kind of the main crater floor unit we call the Maz Formation down there as well. Okay, but here's the data set that I tend to work in the most from orbit, and this is CRISM. This is one of our hyperspectral imaging spectrometers at Mars. This is operating in reflectance spectra, mostly in the shortwave infrared. And so these colors you're seeing here, this is a false color, and it's looking at wavelengths out, between 1 and 2.5 microns. But the color diversity you're seeing here is real spectral diversity that's telling us about mineral diversity. So most of the brown and blacks on here correspond to primary mafic minerals like pyroxene. The red here corresponds to olivine. And interestingly, the green here corresponds to carbonate. And so you can even just see from this very, very simple, 3-band combination that there are very large terrains that have strong carbonate signatures. And in fact, these terrains, you can see that kind of follow just the far western margin of the crater. Those are some of the strongest carbonate signatures we've seen from orbit anywhere on Mars, and also some of the most kind of contiguous signatures we've seen anywhere too. And so it was really the combination of these really well-preserved delta-like features, as well as this very strong carbonate detection that led to Jezero being chosen as the landing site for Mars 2020 and for sample return. Okay, so let's talk about what is in this area, right? So in this area, kind of in northwest Isidis, northwest of the Isidis Basin, it's actually a pretty special place on Mars because it is one of the oldest places on Mars. We see clear exposures of some of the most ancient crust on Mars, which we colloquially refer to as the Noachian basement, but that's a collection of a lot of different things that could have a lot of different origins. What we see, you can see on the left here, this really nice set of figures from Eva Scheller, her 2020 paper, but showing just lots and lots of diversity. We think some of this material is Isidis ejecta, so from that massive impact. And so that could include things like, pre-Isidis material, so stuff dating to the very, very early period of Martian history. It could also include the crust, either shallow or even potentially deep crust or upper mantle. So there's a lot of material that could be in there. Some of it we think is intact basement materials as well that hasn't been maybe as modified by Isidis. We see in those units, we see really strong low calcium pyroxene signatures. That's basically probably indicating more of an ultramafic type composition consistent with kind of a primitive crust. But we also see things that are like layered rocks that have really strong smectite signatures. probably telling us about a pretty extensive alteration of those materials in some kind of aqueous environment. And those two signatures kind of go back and forth depending on what the exact outcrop is. We see megabreccia, that was almost certainly created by Isidis, potentially again from very deep. Some of these same units are found in the megabreccia, telling us they do probably predate Isidis, and they're very old, perhaps more than 4 billion years old. We also might be seeing Isidis melt or actual Isidis, ballistic ejecta as well. The last thing we see that's really interesting in this area is potential signs of post-Isidis surface weathering. We see pretty strong signatures of clays like kaolinite or other aluminum-rich minerals, and that's probably telling us about top-down alteration and weathering under potentially a warmer climate. We see similar signatures all across Mars that we interpret as indicating kind of one or more potentially warm and wet epochs in Martian history. So again, also recording potential surface environments in this area too. The other really important unit in this area, and you can kind of see the distribution of it here on the right, is what we call the regional olivine carbonate unit. And that name is just because those are the main spectral signatures we see from it. It was actually detected originally back closer to 2000 with mid-infrared data showing really strong olivine signatures. When we looked at it with short-wave infrared, we also see carbonate signatures throughout much of this unit. You can see the red stuff in there is where we see the strong carbonate signatures at kind of pretty large, kilometer-sized pixels. And you can see some of the spectra, reflecting spectra on the left. But this is a big regional unit that has a crater retention age of about 3.8 billion years. We know it postdates Jezero because you can see Jezero's down here in the bottom, and this unit kind of actually overlaps onto the eroded northern rim of Jezero. So we know it postdates Isidis, it postdates Jezero, so it's a later unit after the Jezero impact. What is this big regional unit? Some folks have proposed that this could be tephra, some kind of pyroclastic deposit perhaps. It's probably some kind of volcanic unit is a solid hypothesis, but it has some weird properties, like it drapes pretty significant topographic rises, it's thinly layered. Steve Ruff has a nice paper where he compared it to orbital and aerial images of ignimbrites back on Earth, and it has some really nice comparisons. So that's definitely a very plausible hypothesis. It's the one that makes the most sense, I think, from the orbital perspective. And it's altered to carbonate, so it has, and we think that's probably due to alteration in a surface environment. So just to look at a map of where this stuff is, so here's Jezero down here at the bottom right, and this is from Tim Gouge's map of the watershed. So there's both kind of a northern inlet with the watershed and then a western inlet with the watershed here. And so the orange and pink stuff, that's all this deep Noachian basement. The green is the regional olivine carbonate unit. So you can see that the nearby, most of the watershed is this basement. Some of the nearby stuff is this olivine carbonate unit too. And what's interesting from a sort of a habitability perspective is that Nicola Mangold and his group and a few others have done some really nice work looking at when fluvial activity happened in relation to all these units. And they see good evidence that there was basically fluvial incision almost between every single one of these phases. That there's evidence that there was at least pulses, if not ongoing, precipitation, weathering, all of that going on during this whole time period. Again, probably up to the Mayfic cap is the youngest stuff here, and I think that's about 3.7 billion years. So over several hundreds millions of years, potentially at least pulses, if not ongoing, aqueous activity. Okay, so in terms of what did Mars 2020, what's in the crater itself? So here you can see a nice overview of the Mars 2020 Jezero crater campaign. And so you can see we landed out here in the crater floor. And again, the colors here are that chrism map, where red is strong olivine signatures and green is the strong carbonate. So you can see we landed over here at the landing site on the crater floor, a bit farther from the delta than we were hoping, but still we got a great chance to explore this pretty enigmatic set of units on the crater floor. You can see over here. Then we drove around this pretty mountainous, sandy rover death trap. You can see in the middle with the olivine signatures, over to the front of the fan, explored that for over a year, drove onto the fan top, and then made our way across and to the margin. And today we're actually kind of in the middle of the margin unit, heading toward the crater rim. Right now we have some great data from the margin we'll be presenting at LPSC, and we're hoping to get at least probably 1 or 2 more samples in the margin unit before we're done. Okay, so just a quick overview of what's going on in all these different places. So a crater floor from orbit. This stuff, it has these weird lobate margins, it retains craters. The easiest hypothesis from orbit is that it's a lava flow, right? And that was sort of like, well, probably, but Mars tends to fool us, and we see sedimentary rocks that have these characteristics all the time too. So we don't really know. but it's one of the only things in the crater itself that has a well-defined crater retention age, so we can use geochronology of this unit to help calibrate the Martian crater and chronology, and therefore the Martian timescale. On the unit itself, we see a lot of spectral diversity. We see these olivine-dominated hilly regions, which we call the CETA formation, and then these smoother but cratered areas we call the Moz formation. Those are more pyroxene-dominated. Neither one of these exhibits strong alteration signatures, but the CETA area does exhibit some weak olivine and weak carbonate, smectite, and hydration signatures too. Okay. So just to give you a view of what that looks like, here's what that Moz formation kind of cratered surface looks like, and it is indeed a lava flow. We think it's actually a series of lava flows with different properties, probably from an evolving igneous succession. So you can see some of the nice outcrop views of what this looks like, some of the best examples of lava flow-like morphologies. It wasn't all this obvious, but these ones are nice. And then on the right here, you can see, zooming in on one of our lovely Sherlock images, Mastcam Z and then Sherlock, showing this really clear, coarsely crystalline interlocking texture with these big plagioclase lads, telling us that this is in fact a lava flow. And we saw similar properties, at least in the abrasion scale, in all of the outcrops we investigated in this part of the crater floor. So it's all a series of lava flows. So that's great. So we have samples of this that contain evidence for later aqueous alteration. We think we can do some interesting geochronology work on them. And so those are some really valuable samples to start out with. But the thing that really caused a lot of, was confusing when we first landed on the crater floor, was this olivine-rich region. So those kind of red ridges that we saw in the CRISM map. So this olivine-rich region, when we saw it from the landing site, it had these really spectacular centimeter scale, very planar layers. And the sedimentologists said, oh, this has to be, lake sediments or something. But we kept driving, eventually got there, and eventually got to abrade and look at this stuff up close. And it turns out this is, in fact, not an aqueous sedimentary rock. It is more of an igneous sedimentary rock, because it is, in fact, a cumulate of some sort in place from some type of melt body. Right now, our best guess is something like a very thick lava flow or something like that in the crater, a lava lake, maybe something like that. But you can see the texture of it over here on the right. It's all these kind of these big olivine crystals. If we look at the PIXL map, which we might hear about more in a bit, we see some really nice examples of these olivine grains in purple being fully enclosed by these monomineralic pyroxene grains. You can really only do that when you have olivine grains settling out of a melt and then the melt crystallizing around them. So that really can only happen in a cumulate. So then how does this relate back to this big regional olivine carbonate unit? Well, they're really similar compositionally. They both have a lot of olivine. This CETA does show some examples of carbonates and silica and even some sulfates in there, showing it has had aqueous alteration. We found some organics too, which I hope we'll hear about. And that's very similar to the regional unit. It also is layered, right? So there's a lot of similarities, but it's really hard to explain this, hundreds of kilometers in extent, super widespread unit that drapes topography as a cumulate. That's just really, really tough to explain. So the hypothesis that we put in the early papers, and I think still holds true, is that this regional unit is probably some kind of ultramafic volcanic suite with intrusive, extrusive, explosive components, and that maybe CETA is related to it and is sort of an intrusive example of that same kind of magmatic source. But again, alteration story here, organics, all really exciting too, even in these igneous rocks. Okay, going from the crater floor to the fan. So here's what the Jezero crater fan looks like in a nice 3D view from orbit. And so, of course, our big targets at the fan were fine-grained sediments and mineral precipitates, either of which could preserve biosignatures. So the model we had going in from orbit for the fan was that this was a classic Gilbert Delta, where we have rivers running into a lake, dropping their sedimentary load, creating these delta foreset slopes you can see in the beige in the figure at the bottom left, and then transitioning out into these fine-grained lake deposits. And of course, we hope to find these fine-grained lake deposits that would also contain high abundances of organic material. So that was the goal. We'd also take some mineral precipitates in there too to try to preserve biosignatures, but that was the goal going in. And we thought this would be true because from orbit, when folks did a lot of mapping, folks like Tim Gouge and others did a lot of very detailed mapping. They thought they saw a lot of different facies that corresponded to different kinds of fluvial McCushman deposits, most of which you would find in a delta. So you can see in the map over here on the left, so we have these big boulder deposits, which we have now driven through, but these were thought to be perhaps inverted channels or flood deposits or something. We also have these really fascinating looking curvilinear units you can see on the right, where we have these almost looks like, the desert Southwest in the US, somewhere like, Antelope Canyon, where you have these beautiful sedimentary layers, all intersecting, truncating in these curves, interpreted perhaps as river point bars. And then on the bottom here, we have the front of the delta, which was these very, very steep beds, interpreted as possible foresets, and then these very flat beds below them interpreted as bottom sets. So that was the interpretation from orbit. Okay, so was it right? Partly, right? So partly, and I think actually just based on how complicated the system is, the fact that you were partly right is great. So we do see evidence that the fan was clearly partly built by delta activity, or a river flowed into a deep lake, where we have foreset beds at the fan front. So that big steep bed we saw from orbit is in fact this big steep one down here in the middle at the bottom. We do think that is in fact a delta foreset where the river was flowing into a pretty deep lake, probably tens of, maybe not 45 meters, but tens of meters deep for sure. We see smaller examples, this little delta remnant butte in the upper left we call Kodiak. There's some beautiful examples of flat layers just totally turning into these nicely steeply dipping foreset-like beds up the upper right there. So we do see some very clear evidence for that. And in fact, this curvilinear unit, when you see it in 3D, much like in somewhere like Antelope Canyon, right, it is in fact a 3D unit, and a lot of the structure we're seeing in this kind of curvy aspect is because this is a complex unit with steep slopes that's being cut off in different ways. And so when you see it from the side, we can actually see these big buttes like down in this image from Mastcam-Z on the delta, that a lot of these big slopes are in fact these really, really steeply dipping beds that we think are delta foresets, not river point bars, unfortunately, but still not bad. Okay, so the curvilinear unit is also really interesting. It is this delta kind of foreset bed environment. What is it composed of? It is in fact another olivine carbonate unit, layered olivine carbonates, in fact. So an example of where you can have very similar properties in a very different type of material. So here's what it looks like on the right from Sherlock, from the Watson Imager, and on the left, some of our data that we worked with on Mastcam-Z, just looking at spectral diversity at visible near-infrared wavelengths, basically extremely fancy color, right, looking at these wavelengths, and just showing in particular that bottom left image, the magenta color there corresponds to olivine. So it's a nice map of just how abundant olivine is in this abrasion patch. And this is it's about a 5 centimeter across abrasion patch. So there's a lot of olivine. A lot of the blue material you see in there is a carbonate, actually. So it's basically an olivine carbonate and some other stuff mixed in there too. Okay, what else is going on though? So the fan front, this is the one that I think we were all very surprised by. The fan front is generally not composed of fine-grained lake bottom sets. Again, this is the thing we wanted to find to look for concentrated organic materials. Instead, it's mostly composed of sandy and pebbly fluvial deposits. As you can see some examples here, many of which we sampled. So we have great samples of a lot of these outcrops. So we think this is actually an early alluvial fan or fluvial floodplain. It's hard to say fast. Alluvial fan or fluvial floodplain setting that occurred very early before the onset of this kind of deep lake delta setting we see up in the curvilinear unit. So we don't know if a persistent lake was present at Jezero at this time, at the base of the fan. So not the fine-grained bottom sets we were looking for, fortunately. But we did find this one very fascinating horizon. You can see this light-toned horizon up in this image at the top. This is actually a sulfate cemented siltstone, so not a mudstone, not the finest grain thing, but more fine grain than the rest of the delta, and is in fact cemented by sulfate. It also has some of the strongest fluorescence signatures observed to date. And some of the work that my group has done has been looking at the diagenetic history. We see lots of evidence for different, very heterogeneous diagenesis and water interaction across this unit, but there are some locations that actually appear to be still reduced and that they haven't experienced a lot of diagenesis, and that we actually sampled some of those. There's a chance that some of these areas, actually some of the kind of darker zones you can see in the images on the bottom right, are in fact really fine grained. So the main thing we abraded were these kind of paver flat things up here, and those are resistant sandstone, but it's actually possible the stuff just underneath them are layers of finer grain material, and we did actually sample through the paver into the underlying stuff. So we have a hope that in our sample tubes we may actually have some very fine grain material in a reducing environment. So that would be really exciting if that was the case. And of course, sulfates we know are also great for preserving organics on Mars potentially too. Okay, but from orbit, we didn't really know this unit existed from orbit until we saw it. But now looking back, we actually do see evidence that this light tone, fine grade sulfate cemented unit is really widespread. And in fact, we can trace it around almost the entire southern part of the fan. You can see some nice examples on the bottom right there. We think it might be the same facies, kind of slightly higher elevations, but maybe the same stuff. And so we think this could be telling us something important about the delta. Maybe this is a big unconformity related to some standing water and evaporites. Maybe this is or a fluvial floodplain. Maybe this is related to climate change, but it seems like it's a basin-wide deposit of some sort that kind of is right between these kind of fluvial, alluvial, sandy, pebbly deposits at the base, and then the kind of coarser, sandier, deltaic stuff above it. And then top of the fan, we spent a lot of time driving through is amazing boulder deposits I won't talk about. I just wanted to show one image of these coarser, very coarser deposits we saw on top of the fan. We think a lot of this is kind of late stage fluvial activity, flood activity. But what's really exciting about a lot of these units is we see lots and lots of compositional diversity. So on the right here, more of these Mastcam-Z, different spectral parameter combinations, just showing us how much diversity is present in some of these abrasion patches. So not just, they're all carbonate cemented still, but lots and lots of different grains. We see some other things in there too that are really exciting. And we sampled all of these. And so we'll have lots and lots of great samples of all of these different various kind of fluvial units too. Okay, and then last but not least in the crater, the unit right now is the margin unit. And so from orbit, this was one of the units that really drew us to Jezero Crater. And over on the left, you can see why. So this on the left, this is just a band depth map of the 2.5 micron carbonate band. And you can see in the red are very, very strong signatures. And they correspond to, interestingly, actually a pretty narrow range of elevations right around the edge of the crater. And so what this looks a lot like is something like a bathtub ring, right, that you get in lakes on Earth, related to old shorelines depositing precipitates and beach deposits and things. So we proposed in our 2020 paper that this could be, in fact, a sign of authigenic lacustrine carbonates, among other hypotheses too. I mean, there's lots of, as you can see, carbonate is very common throughout the region, throughout the crater. So it's, there's lots of other ways you can make it, but this observation seemed to support that this could be lacustrine in origin. Okay, and of course we're interested in that because mineral precipitates really are one of the things we're looking for to try to sample from our sample return for biosignature preservation. I'm going to keep going. I do want to show this slide though. So I had a student do some really great work out at a possible analog site in Turkey called Lake Salda. It's a magnesium carbonate producing lake that's set in an ultramafic basement kind of lithology. And it's just really interesting to see, what the modern beach deposits there look like. This is basically the analog where we were proposing based on the orbital data. And I'll tell you that the stuff at the upper right looks a lot like some of the abrasion patches in the margin unit. So we're still trying to figure out what's going on in the margin unit, but I think this hypothesis is still definitely in the running, especially something where you have lots of mafic grains mixed in with authigenic carbonate precipitates and stuff. So that's really exciting. And we're excited to see more data coming down from the margin unit. And please come to our talks at LPSC and AbSciCon and 10th Mars. Okay, but just to tie it off, so after the margin, we're going to be still the details of this still a little to be determined with depending what happens with Mars sample return and all of that. But we are planning to explore the crater rim, hopefully get beyond that. And of course, this is really exciting because the Jezero crater rim is where we think we'll get our first chance to investigate in situ the Nowakian basement. We think we've seen a lot of tidal material in the fan coming down from that, but the crust really is the best place, the first place we'll get to see that kind of in situ. And here's just a quick view from Mastcam-Z. This is back on the crater floor across the delta to the crater rim. And so on the top here, you can see this in enhanced color. So you can see lots of dust and sand and rocky outcrops. On the bottom is another one of these spectral parameter combinations, is a decorrelation stretch at longer wavelengths. But basically what this is showing you is a lot of stuff that's very similar to the Nowakian basement outside of Jezero. Kind of magenta colors up on the rim, that's that ultramafic kind of low calcium pyroxene signature we see in the Nowakian basement. You can see it's present in all these little patches up here. The kind of bluer color here it could be olivine or carbonate, so other materials are present here too. And the yellow is really interesting. That either could be this iron magnesium smectite, or it could be something, we see some potential evidence for some weird alteration phases like spinel. And so that's all fun stuff that we'll hopefully get to explore in the coming year or so. But yeah, I think what's really exciting is that even with the suite we have now, and I think this doesn't include the last delta and the new margin samples we have, is that we already have an incredibly diverse sample suite that's getting at big, Mars scale, global Mars scale kinds of questions. We have 3 crater floor lavas of different ages that have hydrothermal and potentially lacustrine alteration. We're hoping to get outside Jezero, maybe this, regional olivine carbonate unit, maybe it's an ignimbrite or something we can date. Maybe it has experienced surface weathering. We also have a cratable variety of sedimentary samples with all kinds of different cements and redox histories. We have these margin samples that are these carbonate cemented, at least the ones we have so far, these carbonate cemented sediments, maybe beach deposits. And then finally, we're hoping to get on the rim itself some possible impactites, impact hydrothermal systems. We see some evidence for that. Lots and lots of really exciting stuff up there too. So anyway, I'll stop there and on to what's next.
Thanks, Briony.
Great. Thank you so much, Briony. That was fantastic. So I will go ahead and introduce Sunanda now, and then we'll have questions after both. So Dr. Sunanda Sharma did her bachelor's, master's, and PhD at MIT, and she is now a postdoctoral scholar at JPL. And so she's, again, on the Sherlock team and can also, we'll also be talking about the PIXL data, and has published many papers on Jezero Crater, including one in Nature on interactions between organics and minerals. And so we look very much forward to hearing your talk.
Thanks, Libby. Can you see my screen okay?
Yes.
Cool. So I'll try not to have too much overlap, but hopefully it'll work nicely together. Yeah, so as I think Briony already showed you a lot of really great images, I always like to start with this just to situate myself and everybody else. And we're in Jezero Crater. This is what it looks like. This was when we were getting into the delta, so 615 sols ago. But it's still someplace that I'm thinking about a lot right now, and I'll talk through some of the data from there as well. So as Briony mentioned, we've gone through a lot of places so far. We started in the crater floor, then we moved to the fan front, upper fan, and now into the margin. And the cool thing about being on this mission is, just a side note, there's so much data that we're collecting that I'm still regularly going back to data that we collected in Sol like 161. So I can keep drawing connections across everything that we've seen up to date. And so I'll be talking about some of the earlier samples as well here, because these are things that are captured in the sample set that we have. So this is where we are right now. So this is Sol 1032 taken by the Mastcam Z instrument. This is what our current terrain looks like. And so going back to the objectives of this mission, so understanding the possibilities for life on Mars was baked into what this mission is. And the part that I've always been really interested in is Objective B, which is astrobiology. So we are tasked with performing astrobiologically relevant investigations on the geologic materials at Jezero Crater. So searching for materials with high biosignature preservation potential, searching for potential evidence of past life using observations that are guided by habitability and preservation, and then understanding more about the geochemical conditions and history of alteration, for instance, that's happened in different parts of the crater. So I think this is stuff that everybody, especially in this audience, will know. But the first consideration generally is habitability. So could life have existed here? Did this location have liquid water, nutrients, energy, and are the chemical building blocks that we think life needs, are those present? And for Mars, yes, there's a lot of good evidence for this. You heard a little bit about that already, so I'll kind of skip through this pretty quickly. And then biosignatures, of course. So are there possible signs of ancient life here? And are there minerals that could preserve biosignatures here? And one thing I want to highlight when I'm talking about Mars 2020 with biosignatures is from the definitions set back in 2013 in the Science Definition Team report. The aim was to find samples that are relevant, interesting, and diverse. They represent the diversity of what we see in the crater, not necessarily finding definitive biosignatures, because that's actually out of the scope of the payload. So the payload at best could find potential biosignatures, meaning things that are of interest for further investigation. Definitive biosignatures need to be studied with terrestrial labs and terrestrial lab instruments. So that's something that we can't quite do, but I'll talk about the great things we can do with the proximity science instruments. So you've already heard about this, we'll skip. Okay, so we have 7 different instruments that are on the rover. You've heard about some of the work from there. I will focus on the 2 instruments that are on the arm. So this is Sherlock and PIXL. They are the proximity science instruments, meaning they get really close to the rock surface. So 48 millimeters or so, for instance, is how far Sherlock operates from a rock surface. And they both work together to study things at a very close detail to get a lot of high spatial resolution data about the geochemistry, the general chemicals, and mineralogy of rocks. And one great thing is that all the instruments of the rover kind of work together across spatial scales. So starting at the largest spatial scale, you've seen things from MassCam-Z and from NavCam, you can see kilometer scale. This is where we are in the crater. And then SuperCam gets to a closer scale of centimeters towards millimeters. And then Sherlock and PIXL, as I said, they're the closest to the rocks, they're furthest on the right end, and so we get to that millimeter to tens of micron scale. So a little bit more about Sherlock. So Sherlock stands for Scanning Habitable Environments with Raman Luminescence for Organics and Chemicals. It's a mouthful, so we say Sherlock. And it has two different types of data that's collected with the spectrometer. So that's Raman data and fluorescence. And these are both different ways of looking at how light interacts with rocks, but you can basically tell chemicals, minerals, and if they're present, certain types of organic molecules. So it's a little bit of a different instrument than has previously been used on Mars to look for organic molecules in particular. And it uses deep UV resonance Raman and fluorescence. So it uses this 248.6 nanometer neon copper laser, and it has about 100 micron spot size with a 10 micron thick annular beam. So 100 micron spot size, and then like kind of a halo that's 10 microns. And these are all the parts of it. So along with the spectrometer, we have two different imagers. So we have Watson, which you've seen some images of it, those beautiful color images that show a lot of rock texture. Those are from Watson. And it has also a name, but it fits with Sherlock, so we'll just keep it at that. And then we have the ACI, which is the Autofocus Context Imager. And this one is co-Bohr sided to our spectrometer. So as we collect data spot by spot, we can put those on an image and actually map to texture. And that's a big thing that we wanted to do with this instrument and with PIXL as well, is observe the rock more or less as it is. So without breaking it down, without crushing it or anything like that, just abrading away, meaning removing the top couple of millimeters and getting underneath that and then mapping it as it's found. So these are some of the types of compounds that Sherlock can detect, and this is from laboratory data. So we could find things like aromatic hydrocarbons. So there's a resonance enhancement effect that occurs when you're using deep UV, where you can see things like aromatic molecules really well, and things like aromatic amino acids. And these are some representative spectra on the left side of what those look like in Raman versus fluorescence. And then we can also see a whole range of different mineral classes. So we don't identify minerals, but we could classify them, meaning like I can't say specifically this is necessarily gypsum, but I could probably say it's a sulfate, probably a calcium sulfate, and you'll see a little bit more about that as we do more of the data correlation. So we can see, for instance, a whole range of different carbonate minerals. And all of this data we collected on our instrument that's above my head, which is why I'm pointing up in the lab here at JPL. So this is what the hardware looks like, and this is what our maps look like. So we do this raster scan pattern, and we usually do maps of various sizes. So we can do maps that are like 36 by 36, we can do 10 by 10 maps, and we can play with the different parameters that we use. And so in a lot of ways, this is a complementary approach to detecting organics on Mars than you may be familiar with from previous missions. So we try not to destroy or alter samples too much, and we can map them right in place. And this means that we can map things like organic mineral relationships. So if you have to crush up a rock and then extract the organics out of it, you won't know exactly which parts of the rock the organics were associated to necessarily. So having spatial resolution helps you figure out, okay, maybe this little pocket of sulfate is where I'm seeing this possible organic signal. And that's what we're trying to do here in order to inform which rocks we should pick up samples from. So this is a little bit more of a live demo of what we actually get. So when I say we have a map on a certain target, this is what I mean. So this is actual data that we have from Mars. So on the right side is one of my favorite targets. It's called Cartier. It has a shape of a sulfate that looks like a polar bear, and this is the polar bear's knee. And so you can see every single point we get these Raman spectra that are on the left side. And the same is true for fluorescence, but when I tried to put them both on the same slide, PowerPoint crashed. So on the left side, you'll see the Raman data. And not every single spectrum has a resolvable peak that we can definitively say, oh, it's this type of mineral, but there's a lot. So even on this last one, there's a peak that's right around 1005. That's probably a sulfate. It's on a whitish mineral. And then you see a OH stretch that's happening down here. So that's how we do that type of identification or classification. And then this is PIXL. So PIXL is the planetary instrument for X-ray lithochemistry. And so they collect a different type of data, which is X-ray fluorescence. And so they work closely with Sherlock. They also do fine scale observations of rock surfaces, and it basically measures elemental chemistry at a smaller than millimeter scale. So it uses a focused X-ray beam to generate fluorescence that's then analyzed in order to create these beautiful elemental maps, which you can see here on the right side. So this is some of the first data that PIXL got down. So you can see basically broken down by different elements, you can see the relative elemental abundance in a certain area of interest. And so it also has a camera, which is the micro context camera, that allows that elemental data to be mapped onto an image of the rock texture. So you can get a geochemical understanding of a target of interest. And it can detect a range of different elements like sodium, magnesium, iron, chlorine, all that kind of stuff. Not so much the lighter elements. And it can also detect trace elements like yttrium. And so this is the view that the proximity science instruments have as we're getting closer and closer. So you see we get to that tens of micron scale, and this is an example of our first abrasion patch, which is Guillaume. And this shows the multiple views that Sherlock has with its two different camera subsystems going down to this last one, which is the ACI. And so this is where I normally look at rocks. So if Briony's looking at the really big picture, I'm looking at like the really, really small picture most of the time. And so the resolution of the Sherlock context imager, as I said, is 10 microns per pixel, and the beam size is that 110-ish microns. PIXL is 120, so we overlap fairly well, and we try to overlap our scans as well to get as much complementary data as possible. So this work is from a paper that we published a couple of years ago from some of the targets that we looked at in the crater floor, Bellegarde and Dor. So on the left side, you can just see a comparison of the PIXL high-res scan versus the Sherlock survey scan and the Sherlock HDR, as we have different modes, and how we tried to overlap on Bellegarde and on Dor. And so this is what we get from correlating data together from two different instruments that use different techniques. So from Sherlock, we saw, based on the position and the positions of the Raman peaks, we thought that there was probably olivine, carbonate, sulfate, silicate. Silicate is tricky for us to detect because some of the primary peaks would be below our lower edge filter. And we saw some amount of OH stretch indicating hydration associated with one of the sulfates. And then from PIXL, we have elemental abundances indicating that there's magnesium, calcium, silica, iron, and sulfate. And these are present in the overlapping scan area. So you can see sort of how we tried to draw those out in the two different types of maps that we have. And so this means that we can mutually confirm that there's sulfate, probably iron-rich olivine, pyroxene, and carbonate. And so, for instance, PIXL can't detect carbon directly. They have to do it through a slightly different method. Sherlock can detect carbonate directly. So in this way, we can mutually confirm what we're seeing. And so going a little bit more into this target, because I think it's actually quite interesting. So this is in that Seta region that Briony mentioned earlier, which was the complicated one with the olivine accumulate. And so this target, Dorb, we did several different scans on it, as you can see. So on the bottom left of the image here, there's 3 different scans. And you can see not every single one of those circles is filled in. This is sort of our identification map. That just means we didn't find peaks in the spectrum that we were able to clearly resolve and identify what the mineral is. But a lot of them we actually could resolve and figure out what we think the minerals are in each case. So we saw detections, as I mentioned, of the olivine, carbonate, pyroxene. We saw something that looks like a perchlorate or a chlorate, possibly co-located with sulfate, other silicates, and then that sulfate in hydration. So what does this mean? So we had this hypothesis that this Seta unit is an olivine cumulate that's exposed to at least one aqueous alteration event. This could have led to partial carbonation of olivine, and these sorts of carbonate rims were found across Seta in 3 different targets. So could that mean that there was the same process that affected multiple rocks in this area? So a little bit of olivine carbonation, and then maybe a sulfate-rich brine came in and then filled in these little pore spaces, which is why we're seeing these pockets of sulfates. So this is how we're sort of moving forward our hypotheses based on the data. And this is the target on the left side, this abrasion patch, and this is what one of the samples looks like from it. So this is Coulette. And then these are the 2 samples that we picked up, which was Coulette and Salette in their actual cache cam picked up little samples. And then I'll just speak really briefly about organic molecules. Do I still have time? I don't know how much time I have. I'll try to wrap it up really fast. I'll just brief this really quickly. So one of the things that I've been the most interested in is using Sherlock data to try to find if there are evidence for organic molecules present in a bunch of the different targets we've looked at. And this is tricky because, as I mentioned, DPV Raman is kind of a new technique. It's kind of a different technique, and we don't use it even that commonly in Earth labs in planetary science. But organic molecules are important because they exist sort of at this overlap between habitability and biosignatures. So organics are not necessarily caused by life, but they do give us some indicator of habitability. And so in the work that I did published earlier this year, I went through 10 targets in the crater floor and categorized basically all of the data that we had collected, both in terms of the fluorescence and the Raman. I found 4 different categories or groups of fluorescence types, and these match somewhat to what some of the organic molecules that we have in our laboratory standards look like. However, that's not the full story, because of course we have to see what are the other possible hypotheses. So recently I've been looking at what non-organic sources could cause these signals as well. So I had listed out a few different hypotheses in my paper. So things like rare earth elements in sulfate, for instance, can cause some types of these luminescence emissions. So some of the work done by Svetlana in 2018 points to this in phosphates. I'm looking at sulfates now. And some previous work done as well by Gaft. And then of course, mineral defects can also cause these sort of color center emissions. And so these are things that we're looking into further now. So there's a lot of ongoing work with all of this data because this represents thousands of points just in 10 targets. And then I've started to pull apart these fluorescence mineral associations. So a lot of those minerals that I brought up previously, this is where we're seeing really strong fluorescence in sulfates, in carbonates, in phosphates, and in some different types of silicates. So I think I will leave it there. Blah, 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 blah. There's lots more stuff. We have a lot of cool samples. We've tried to represent the diversity of everything we've seen in the crater so far. We picked up 9 samples in the crater floor, 9 in the delta front, 3 in the upper fan, 3 in the margin, and hopefully some more. And we really hope to be able to get these back to Earth in order to answer all of those big questions that are still lingering out there that we've gotten so far with our payload that's currently on Mars. So thank you.
Thank you so much, Sunanda and Briony. These were really fantastic talks. So now I think we can open it up to questions and discussion. Do folks have questions for either of our 2 speakers?